I think the up and down.
We're trying to show that this can work.
Okay, everyone, so we're very happy to have Victor Gorbenko from Stanford today. He's going to tell us a bit about the analyticity and unitarity for cosmological correlators.
Hi, thanks, Edward. It's great to be in Chicago in person, especially. It's probably the first seminar I'm giving in the US in person since 2 years ago. So yeah, it's going to be a talk about cosmological correlators. We'll start a little bit with a general motivation. And I'd say, I don't know, maybe status of physics in the de Sitter space. And okay, that will be something vague in general. I guess most of you are probably not thinking about cosmology or the de Sitter space all the time, so I'll try to review at least from my point of view where we stand and what are the big questions. And then we'll switch to something concrete. We'll discuss some results. Okay, since you're recording this, I also have to give some references. So this all results are in the paper of me and Shota Kamatsu and Lorenzo Di Pietra. And there will be the following, just expanding it in a few more details. So there will be some computational tool, which is a rotation, some continuation that I will explain from de Sitter to Euclidean anti-de Sitter space. That would allow us to do some concrete calculations, and there is also related work on Slate and Tarona through the past few years. They wrote some papers that are closely related to this thing. Then this tool basically will allow us to do some calculations and study some basic analytic properties of these correlation functions, and that will we will discover some sort of operator product expansion, or discuss and analytic, like I said, analytic structure. And then we will focus on the 4-point function, okay? We'll be all about the 4-point function in cosmology. And then the third type of results will be related to unitarity. Okay, so we'll also want to see how unitarity encoded in this cosmological correlation functions. And that will come as often unitarity comes as some sort of positivity. So positivity of certain spectral density with respect to conformal partial waves decomposition. I will introduce, well, briefly introduce what is conformal partial waves, in case you don't know, and then there is some expansion with respect to this conformal partial waves that carry some positivity problems. And this results related to unitarity also appeared in a paper of Pinidonis, Valisi, and Hogervorst that appeared even a little bit earlier than our paper. And then, if there is any time left after this, which I doubt, we can discuss maybe some lessons and future directions. Basically, what this all results teach us about the original motivation. That's roughly the plan. First question is that, is it large enough, too large, too small, especially for people on Zoom, or all right?
Fine in the back of the room.
In the back of the room is fine, okay. I assume that, okay. If something is unreadable or invisible, tell me. Okay, also, doesn't really matter through how many of these I get. If you have questions, interrupt me at any time. We can discuss more, benefit from me actually being here. Okay, let's start with this, the motivation part. So we're going to study de Sitter space, and actually in this talk I will de Sitter or quasi de Sitter space, so just cosmology more generally will be roughly the same thing for me. Okay, but still, let's start with some observations. So if we look in the sky, then we see that universe is on large scales is very isotropic and very homogeneous, and also approximately flat. So basically, the metric of our universe can be written in this form, okay, where this A of t is a scale factor, okay, it describes how universe is expanding. So now, if we also look at our universe in some telescope, then we can also see how this A of t depends on time, and we will see something roughly like this. So there are two pieces, namely over here, which is kind of close to our current time. So this is t equal t0. This is where we live now, and over here, where the universe is expanding almost exponentially fast. Okay, so this is the period of current expansion with the Hubble constant, celebrated Hubble constant h0, and this is the period of inflation, which is okay, is not directly observed by experiment, so it is still a conjecture, but still the a conjecture that has a definitely huge amount of experimental motivation. Let's put it this way, where again the universe was expanding approximately exponentially. Okay, so now if we plug in this exponential scale factor is exactly an exponent, so that gives us a metric of the Sitter space, which will be the main subject of this talk. Okay, so now this experimental picture it not only motivates us to study the Sitter space, but it also gives us two, I would say, complementary views, two fundamental views on the Sitter space. So to explain those, let me also draw the Penrose diagram of the Sitter space, which looks like a square. Okay, so when I guess more formal people talk about the Sitter space-time, they usually draw this square as opposed to trying to draw this plot. And when people try to understand fundamental properties of the Sitter space, there are two schools of thought. One school of thought is, well, let's say, local versus global. Okay, so the local school of thought tells us that we really need to study only what is called the static patch of the Sitter space, which is this triangle over here. Okay, so this is the static patch. And this is a part of the Sitter universe that is seen by a single observer that travels around this line. By the way, I kind of said Penrose diagram. I assume people know what it is, but if no, let me just say that the Penrose diagram is a way to draw this infinite space-time as some compact picture which preserves the causal structure. So the light still travels at 45 degrees. So this 45 degrees line, that's a horizon, right? So if a guy lives here, because the cosmological horizon, he cannot see what's going on here. He can see and communicate with this triangle, okay? And this is basically how we are now. So now we are, if we say, assume that our universe is actually exactly the Sitter, which is it's close, but let's say it's exactly, we are like this guy now, and we see our local Hubble patch, which is huge, you know, billions years large, but we see this finite piece of this exponentially expanding universe. On the other hand, the global school, it likes to study observables that live close to this future boundary of the Sitter space. Okay, so so we can imagine that there are some fields that live in this Sitter space, and then we measure their correlation functions pushed very close to this infinity. Okay, so we insert some sources, some fields, and we can calculate the correlation functions that live over here. Notice that the no single observer can actually see this. However, when we look back in our telescopes on our universe in the past, we observe this this period of cosmological expansion, we basically can see its future boundary. Well, the way it happens is that this de Sitter space is not determined, it actually terminates. Okay, so in this global picture, what happens is that the Sitter space gets cut off a little bit and then transitions to something else, to some FRW universe, which is basically, we can roughly say that it's almost like a flat space. And then there is a person like us, say this is our Planck satellite, that looks back and sees almost the entire future boundary. Okay? So this is the global point of view.
The Sitter space, what is the global, and what is the interpretation of those global correlators?
Well, as I said, in the full eternal de Sitter space, it's sort of not so clear. Now we need to, you know, let's call, I learned it from Dio, this word, Dio is calculables. Okay, there are observables and then there are calculables. Okay, so let's say that something that first we want to calculate, we can calculate, and then this is the debate. Yeah, do they have to have some fundamental meaning or not? These are basically what these, you know, philosophers from these two schools of thought like to argue about. But for this talk, we will not argue about it. Maybe not until the last point. We just say the following. There is first a phenomenological motivation to actually calculate and understand these things, because with very good approximations, us now are like a quasi-observable for this early de Sitter space that actually sees and measures these correlation functions. Okay. And then two, well, maybe it is a way to define the de Sitter space fundamentally, even though, you know, there is no single person, no single physical observer who sees this. That's all I can say for now. Good. So okay. So this talk will mostly consider this global perspective. There has been several developments in this local point of view. Lenny wrote several papers. Say Eva Silverstein has pursued this idea in a slightly different way under the name of DS correspondence, but morally, I think it is this local point of view. Also together with Edward collaborators, we together with you wrote some papers about this, but I'm not going to touch upon in this talk. We're going to talk about this global point of view. Now, in this global point of view, often what's mentioned is some term which is DS. I should write like this: DS CFT correspondence. Let me tell you what that is. So let's write down the metric of the Sitter space in the following form, which just amounts to going to conformal time as compared to that metric. And then you see, okay, maybe I put Hubble over here. You see that this metric is very closely related to the metric of anti-de Sitter space. If I just take eta to IZ, then we get something like up to a minus sign that maybe for a second, or maybe we do this also H to I 1 over R. Then we get, and actually, yeah, let me just set it. For the rest of this talk, I will set Hubble to 1, okay? So I will not be writing it anymore, but for here it's kind of nice to still have it, because we see that we also need to analytically continue the Hubble constant and the time coordinate of the Sitter space to get the metric of Euclidean AdS space. So now, because of this, this future boundary of de Sitter space looks much like the spatial boundary of anti-de Sitter space. And then people said, okay, why don't we, and then people is Strominger, Maldacena, Witten, why don't we start try to apply tools similar to AdS CFT correspondence and define some CFT that is produced by this de Sitter space. So one important thing that I want to emphasize that this DS CFT, it is a science, this tradition, it is a science about the wave function of the universe. Okay, as emphasized especially in the paper of Juan on cosmological on an almost phenomenological paper of Juan on computing inflation in non-Gaussianities. Good. So this wave function. So why am I saying the wave function of the universe? And importantly, this is not what cosmologists measure. Okay. The reason is the following: that in AdS CFT we usually we fixed the boundary conditions at the spatial boundary of untitled de Sitter space, and if in de Sitter instead we fix the boundary conditions in the future, then this means that we are calculating the wave function. Okay, so the path integral with fixed boundary conditions on some Cauchy slide, it computes for you the wave function. So to go from the wave function to correlation functions, so cosmologists, they actually measure correlation functions, say of some field, let's say there is some scalar field phi, and we want to measure its correlation functions, one actually need to take another path integral weighted by the wave function that is an object of calculation in this DS CFT. Okay, so that's just to say something that there is a subtlety, I will call it important distinction between the types of observables that we want to calculate in cosmology or in de Sitter space, and that routinely compute in the case of AdS CFT. Good. Any questions about this type of big picture and where we are? Okay, good. So this is it was like a very broad review of the Sitter space. What we want, what we would like to do, we would like to have some fundamental description of this kind of spacetimes, and the point is that, well, okay, so far we have none. So we have none because if we put gravity, dynamical gravity in this type of spacetime, the only way we know how to describe gravity fundamentally is by some holographic idea, and there is, okay, there are proposals, but neither for this type of thing, nor for this type of thing, there is no really working idea of how to set up holography for cosmological spacetimes. Okay, we can say in this language, if we go from the DS CFT direction, the problem is that we in particular need to integrate over the metrics of the source for the stress tensor, which is like some three-dimensional metric that lives to the boundary. So this, when we go from DS CFT to say correlation function, we still need to path integrate over metrics. So there is still some dynamical gravitational theory that we need to solve, and we kind of do not, generically, we cannot solve some dynamical gravitational theory without using some other layer of holography. Good, so now, from this motivation, what I'm going to do, I'm not going to get anywhere close to such a fundamental description. But what I want to study in this talk is just to study quantum field theories on a rigid de Sitter space.
Victor?
Yes?
How far have people gotten of just thinking about saddle point approximations to the gravitational path integral in that context?
Not very far. Not very far. Because there is, it's not even clear what your saddle point is, I would say, because so we don't want, like, it's not even very clear what to say, what is, asymptotically de Sitter space in a proper way. I mean, you can mathematically you can write, say, down what it is, but it's not clear why your metric would want to be close to de Sitter in the future, because you're not allowed to fix it, right? So not very far. Of course, once you have inflation, that's what people do if you want in practical inflationary calculations, right? You always use some saddle point approximation, and then you are, non-Gaussian is a small, perturbation is small, so that's what you do in inflation. But the difference in inflation is that you have a clock field, which is an inflaton, and it kind of gives you, at least tells you, gives you some simplification. For some gravity in pure de Sitter space, I don't think there is a very understood precision, even in the semi class. which I'm not saying it's not good. I think it's a very good point to try to work out. I don't think anybody worked out. So status is really that little is known, and especially little compared, there's always lots of work has been done, but very little is known compared to what we know in flat space or in Analyticity. And what we decided to fix it is one line of attack on this is to first understand just quantum field theory on rigid de Sitter space. Okay, and it turns out that again very little is known even about this subject. So the idea is that ideally we want to get there to understand some fundamental description of our real world space-time, which is close to the Sitter in some space. But first we want to just do quantum field theory. That's what this talk is going to be about. All these results are results for quantum field theory on a rigid de Sitter space. Good.
Continuation to some kind of AdS.
Yeah.
If your de Sitter was not eternal, what would happen to that?
Well, yeah, good. So then it's like we're calculating. So when it's eternal, right? Then we are even in AdS, in DS it would amount that we calculate our correlation functions. Note so this is eta equal to 0, right? Instead, we'll be calculating them over here. As I said, that was eta to 0. I erase it. This is some eta equals, say, eta c, which is very small. Then if we analytically continue again, we get some cutoff AdS space, roughly speaking. So then, we had some finite distance away from the boundary,
I would say like some kind of finite cutoff.
Yeah. It's a similar. Will be similar effects to finite cutoff, modulo, of course, this complication that also, we need to do this extra integral. But say if we just calculate the wave function, say the first step, for example, then it's like calculating with a finite cutoff in AdS. Other questions? Good. Okay, let me tell you what I think the simplest way to tell you what I want to do, okay, for understand QFT in the de Sitter space is just to give the analog in flat space. So let's do first a flat space recap. So say in flat space I can take some theory. Just let's take a theory of two scalar fields. Okay.
Does the board maybe go down a little further? So I think the top line might be a little hard to read.
The eraser is in the way at the bottom.
Yeah.
Oh,
yeah.
I see.
Well, that erases something on the left.
It's like
better?
Yeah.
Okay. Good. I'll try to not to write something very important close to the top. So let's take just theory of two scalar fields that interact with, say, cubic potential. Okay, so sigma is maybe like a heavy particle that can decay into two light phi particles. Have something like this in mind. Okay. Then what we do when we calculate some tree-level amplitude, okay, and that is given by something like 1 over s minus m sigma squared. So the phi particles, interacting through the sigma particles. Good. So this is the amplitude, and say it's some contribution, but say I'll just call this this is an amplitude that depends on s center of mass variable. Then we can look at the analytic structure of this amplitude as a function of s, and then we will discover a pole over here. So now, if particle sigma is large enough so that this pole is in a kinematically allowed region, then we will understand immediately that this violates unitarity. Okay, because unitarity tells us that the absolute value of amplitude squared should be smaller than 1, and this thing just blows up. Okay. Then, well, we understand very quickly that what we need to do, we need to actually resum some sort of diagrams like this, right? Resum the propagator, and this promotes our amplitude to something which is like 1 over s minus m sigma squared minus this capital sigma of s, where capital sigma of s is basically the value of this bubble diagram. And this thing develops imaginary part. So instead of a pole, we're going to have a cut over here, and then this pole will be somewhere on the non-physical sheet. And again, if this is a simple calculation you do, in your first QFT course, but it has lots of interesting physical information already. For example, the imaginary part. So there will be some imaginary part here. It has to be positive, and this is unitarity, right? The absolute value of the AdS matrix is still smaller than 1. That is still unitarity. Now, if we actually plot, if this pole is somewhere close, and we plot our function over here, then we see like a resonance peak. There is a width of this resonance. It's related to lifetime of the party. So there's lots of physical information that we're kind of used to, but that is very appears that is very non-trivial actually, and it appears in this simplest example. So these are kind of things, and also we know that there are no singularities in this, on the physical line, and there is some analyticity on the physical sheet that is partially known, partially not known. So lots of science here about understanding properties of this relatively simple diagrams. So these are kind of things we also want to understand about the Sitter space, and the claim is that our understanding even of these basic properties and what resonance means is lacking. Okay, good. So now what I'm going to do, I'm going to prove or discuss some general properties, but the theory that I will have in mind for this talk, like my main working example, will be the same theory, but just put in the Sitter space. Okay. So have in mind the following setup. So we have this theory of two fields, and say again phi is a lighter field. And what we want to do, we want to take out the Sitter space, insert some of these phi fields very close, so actually on its future boundary, and then calculate the what are the correlation functions of, say, this 4 phi fields. Okay. So first thing is that since these are correlation functions, these are what is called in observables. As opposed to this the amplitude calculation that I just erased, which is an in-out observable. So what this means is that to calculate this correlation function, okay, maybe let me first. This. I need. Okay. This. And then I can do this. Okay. So to calculate this correlation function, we need to take some initial state. Okay, that there are some actual debates about initial states. There is a singled out initial state that is called Bunch-Davis vacuum, at least for quantum field theories on the Sitter. Within perturbation theory, at least, it's definitely easy to define, and actually non-perturbatively, I think one can also define what it means. And in this state, we evolve this state, say with the interaction Hamiltonian, then we insert our fields, and then we evolve the. So this is the bra, we evolve the cat of the state, okay? And then in this state, we perform the calculation of our correlation functions, right? And actually we evolve all the way to eta equals 0, or time equal infinity. I use, where's conformal time now use. Okay? From eta equal minus infinity. Sorry, this is small, but I mean, I hope everything. everybody understands what it is. Good. So now if we insert this interaction Hamiltonian over here, we will get several types of weak contractions, right? So we will have roughly some diagrams of this sort. So on my diagrams, time goes upwards. It's still same diagram. Okay, so these are 5 particles exchanging a sigma particle, but now actually there are 3 types of diagrams with this topology. Because I can pull out the interaction vertex from the left Hamiltonian, say left, or I can pull one interaction vertex from here, one interaction vertex from here. That will be what I call left-right, or I can pull both interaction vertices from here. Okay, right. So there will be 3 types of propagators over here. Okay, so that's first a little bit of a complication. Now, this propagator, G, say for this particle, whatever, for any particle, let me call it G nu. It turns out that it is some sort of hypergeometric function. And well, because I have this 3 different propagators, I label by some value alpha, and actually the only thing where this alpha enters is in this I epsilon prescription instead of my hypergeometric function. And this S is some measure of invariant distance between 2 points in the series space. So I wrote down this propagator in the position space because actually we will be doing our calculations in position space. You can also write down what it is in the Fourier space. Or some subtlety. Never mind what it is. The point is that there is no, like if you just write down this expression for this simple 3-level diagram, there is no simple way to evaluate it. Even this 3-level diagram. So this 3-level diagram was first time analytic expression was obtained like like 2 years ago, something. This paper is by Slate and Tarot. Okay, so this is kind of the status. So. Well, in analogous AdS calculation has been known, a long time ago. And the complication is that there is no simple Fourier transform that would factorize this integral, right? Because what made it so easy to do this calculation in flat space, that was the Fourier transform. Problem is that in the zeta space, we can do Fourier transform with respect to, say, the spatial directions because there is enough isometries, but we cannot do a simple Fourier transform with respect to time because the metric of a spacetime depends on time. So there is no simple Fourier transform that factorizes even these simple Fimon diagrams and allows us to calculate. Okay? Good. So that was the complication. So this brings us to, to me, basically stating the results of this first of my results is that the claim is the following, that any Fimon diagram in the zeta space.
Sorry, Victor.
Yes?
The expression top line, is that e to the h interaction?
Yeah. Let's go to interaction.
What about, like, can I not do this in a free case?
No, sorry. In free case, you can calculate all the correlators. Yeah, they will be just like mean field theory. Yeah. But if we have some simple interaction, okay, more or less the simplest interaction I wrote down. Then okay, we need the.
And the difficulty is doing the integral in the zeta space.
Yeah.
The eta direction.
Yes. The integral is the complication. The hard technical part is doing the integral in eta direction. So as I said, I do these calculations in the position space. Some people do it in the momentum space with respect to 3 dimensions and then real time. Slate and Tarona do some Mellin-Barnes representation of this integral there, but the bottleneck is doing the time integral.
The complication isn't some physical principle. It's just like I don't know how to do this.
Yeah, the complication is that we have, as compared to say analogous AdS calculation, that say in momentum space we have like some theta functions of time because they actually time ordering, right? Because by the way, I should have been careful. I mean, I should put it like a time ordering exponent here And time ordering explained that was kind of explicit, right? And that this time ordering makes the integrals more complicated because you need to calculate integrals in time, but also with some theta functions. Or in this position space, okay, then there is I have some prescription that again makes the integral complex and complicated. Other questions? But the claim is that any diagram, I'll write it here. Any Fimon diagram, any set of Fimon diagrams. Okay, so you take some theory, you take your set of Fimon diagrams at a given order in the coupling constant. In DS can be generated by a Euclidean AdS Lagrangian. Okay, so this is the statement that is true to perturbatively, but to all orders in perturbation theory. Okay, I'm not making any claim non-perturbative, but any set of Fimon diagrams, any order, can be generated by a Lagrangian that lives purely on Euclidean AdS space with a doubled field component. Okay, so here I have it written. I hope everybody can see. But okay, the first line is simple, but you cannot see it. So here I just wrote a theory for a single field phi with some self-interaction. Okay, it can be generalized to any number of field and interaction. But let's take some single field phi with the with some potential self-interaction, and we replace it by a theory that lives on Euclidean AdS space that now has two fields, phi plus and phi minus. Okay, it's seen as a weird-looking Lagrangian with some complex terms in it. Okay, but you take it, so it is non-unitary from AdS space point of view. You calculate all your Fimon diagrams directly in AdS. Okay, there is no time ordering; it's a Euclidean theory, and you generate the sum of all diagrams that you get in the zeta space. Okay, so that's the claim. I'm not going to talk about the proof in the talk, but because I don't have time.
But it's non-local, there are derivatives and exponentials?
No, sorry, yeah, there is, okay, yes, that's my poor handwriting, yeah. There is nothing as crazy, no. It's just a potential interaction still. This nu, I think that's the problem. I didn't say what nu is. So nu is just related to the mass of the particle. It is just a square root of m squared minus d over 2 squared. Again, I mean, people who do AdS calculation, sorry. Nu is just a constant that is related in a simple way to the mass of the particle. Okay, and it's this nu that appears in all these cinches and all these exponents inside of the potential.
And this is for the Bunch-Davies state?
Yes.
Can you generalize, I guess, for a density matrix?
That's a good question. Yeah, it's this. As I said, this is true for this Bunch-Davies states. It's important which state you pick, of course, because here there's no longer state. I mean, there's no way to input the state. It's just a Euclidean calculation, right? State is given by some propagators and anti-de Sitter space are defined by being continuous in the origin of anti-de Sitter space. Okay, so this is true of Bunch-Davies, and it's interesting to see what happens with some other potential states. But let me finish explaining the prescription. There is two fields, phi plus and phi minus. Okay, now for a single field on the Sitter space. Now these two fields, to again do the calculation under the Sitter space, one needs to specify the boundary conditions for your fields. And these fields phi plus and phi minus. So if we take some, if we take our, say this is Z of my Euclidean AdS space, the field, and if we put some scalar field phi, then when it approaches the boundary, it will have two types of behavior. There will be z to the power delta plus and z to the power delta minus. And this delta plus and delta minus are just z over 2 plus minus I nu. So Okay, so there is some familiar to at least some people. Example is when we take a scalar field slightly above the BF bound, and idea is then both boundary conditions are allowed. Now here, because we are talking about theory that is non-unitary from AdS point of view, the claim is that at least operationally, for any field, both boundary conditions are allowed, and we need to take one field with plus boundary condition that is called phi plus, and another field with the minus boundary conditions, and combine them together and also make them interact in this particular way. So potential depends on some linear combination of phi plus and phi minus, so now interactions between those two, and that will produce the right structure. Okay.
There's only one quantization, unlike in AdS.
There is only one
set of boundary conditions that will reproduce what you want out of.
Yeah, you see, in DS there is no boundary condition. We specify the state initially, right? So that's what we're talking about. I found a way to specify it with some IF prescription. Basically, it is done here. Okay, so the bunch of the state is a state that at short distances looks like Minkowski vacuum, and the Minkowski vacuum is unique for this theory. But anyway, so there is some state conceptually. Say we define a state, then we evolve it in the future, and then we calculate its correlation function. But with not fields can be anything in the future, right? That's the point. That's also the point of basically this integral, right over here.
So you'll tell us what that means in terms of you're imposing something on the correlation function, I suspect, to say, like you say, there's no boundary conditions. There is some way of describing, setting the bunch Davies, and then you evolve. You have no say in what the fields do.
Yes.
I understand. So, does that translate into a statement you're gonna impose on the correlation functions to compute, or?
Well, no. That's the physical question, right? We take a state, we evolve, and then we calculate what the correlation is, right? It's not so exotic. It's any inner conclusion in say condensed matter physics, so that's what you would do, right? You have some state, maybe thermal state, time-dependent state, in this case. It's explicitly time-dependent. You evolve and then you calculate, right?
I think indirectly I'm asking where that Lagrangian came from, but maybe that's not.
Where this, this is.
Yeah, we can.
Oh, you can ask me where this came from. Yeah, okay, that's what we can. Let's skip that because I will not have time to say anything else. I'll tell you after.
What's the boundary metric in your Euclidean AdS?
In Euclidean, it's just a rigid Euclidean AdS, say with this metric. Say with the
plus time. We go to Euclidean. You want to?
Euclidean AdS, say this metric. We can be big for Euclidean. It doesn't matter, but let's use Poincaré coordinates.
You don't care about the global.
I care initially about global de Sitter space.
Right, but here you don't care about global AdS.
Euclidean AdS is only one, right? I can use any coordinates. That's the trick, yeah. In de Sitter, there is global, there is Poincaré, there are many different things. You calculate, things are complicated. The claim is that whatever you want to calculate, as long as the observable is restricted to the future boundary of the de Sitter space, you just use this Euclidean AdS Lagrangian. You forget about the fact that there were different de Sitter spaces. You just do this calculation. It's unique, well-defined, and you get the right answer. That's the magic, okay? Good.
So if you're interested in computing the wave function instead of correlation function in this from this Lagrangian,
Yeah.
then I guess you can just keep one of them.
If you good, yeah, that was basically as pointed out in the CFT literature. If you were interested just in calculating the wave function, that yes, it's just you just analytically continue a single copy of your theory. You don't need to do anything that fancy with Lagrangian. Here it's a bit more non-trivial because you have three different propagators in the de Sitter space, and somehow. And here you have two fields and two different propagators for them because this propagator depends on boundary conditions you have in AdS. And somehow this theory with doubled fields and two types of propagators reproduces the correct sum of this theory with three propagators. Good.
I mean, can you translate directly? Do you get identities on integrals of hypergeometrics?
Yeah, okay.
Or
let me, since you guys are asking questions, let me explain a little bit and then I'll make this part really short. It's not, that involved the proof. The thing is that, of course, what you want to do, let's say in the de Sitter space, we also use Poincaré coordinates, just for simplicity, okay? So now we have this, we take this diagram, and there are this, you know, d eta 1, d eta 2 integrals of some stuff, right? Where this eta 1 and eta 2, that's a time insertion. So now we want to analytically continue these etas to e to the I plus minus pi over 2 z, and this plus minus depends on epsilon prescription. Okay? So left, if eta is a left time, we rotate one way. If eta is a right time, we rotate the other way, depending on what this label is. Okay? So now what happens is that we can track how these propagators get analytically continued, and we see that they can always be replaced. They get analytically continued, you know, you use some identities with hypergeometric function, but then it's also surprising that they can be expressed as a linear combination of two AdS propagators, and there are basically only two solutions of the Casimir equations, which AdS propagators with these two different boundary conditions. So then what you do first is that you replace this theory with a series of 4 fields. And that's almost guaranteed to work. What are the 4 fields? You have one field, you have a left field, a right field, that's like Keldysh doubling, okay? And then also for each field you have 2 AdS fields because you express as a linear combination of 2 boundary conditions. Then you look at what you get and you see that the matrix of propagators for these 4 fields is actually degenerate. And 2 fields completely decoupled. And then these 2 fields, phi plus and phi minus, that you get, there are some linear combinations of kind of 2, you know, say plus and minus Keldysh fields, and an extra doubling due to different boundary conditions. So that's how it happens, okay? And maybe, so it's a bit of a kind of, I don't know, just practical way of thinking. Maybe there is some more physical way of to understand what's happened, but that I don't have for you. But what I have is this just, you know, diagrammatic proof that it works this way.
How did the cinch come? So the d phi is in the cinch?
Where did these cinches come from?
What's the argument of the cinch? Oh, it's just
Phi nu.
Oh, okay, sorry. No.
It's not, yeah,
I was worried. Okay.
Yeah, no, this news just come from some. When you analytically continue these hypergeometric functions, you get some e to the pi news all over the place, and that's how they appear.
If you take the flat space limit of de Sitter, what happens on the AdS side? Does one of the degrees of freedom decouple?
Good question. If we take flat space limit, yeah, that's a good question. You need to be. It will also depend on how you want to take your flat space limit. If you want to keep masses finite and that will of course change scaling. But if you keep masses finite in AdS radius, yeah, I didn't look at it. Something, of course, what you will reproduce correct flat space physics. And indeed, you can do it with one field. And actually, we wanted to look at it, like what's the analog for like the S-matrix calculation. But yeah, I do not know. Again, it is an in flat space calculation that we will produce, which is in flat space is more simply related to in out, right, than here. But yeah, I didn't look in details how it happened. Other questions? Okay. Then let me tell you, okay, I don't want to hold people longer. I'll just explain again the statement of these two as quickly as I can. Actually, yeah, I have another equation prepared for this.
Also started 5 minutes late.
Yeah, no, it's fine. Okay. Needless to say that the symmetry group of this of Lorentzian de Sitter space is the same as that of Euclidean AdS space, which is as SO1 comma D. Right? So now it means that this correlation functions, they should have some, well, they transform in a proper way under this symmetry. So this implies that we can do the decomposition of correlation functions into conformal partial waves. Okay, so what is this conformal partial wave? Because I want to be brief, I just say the following. This is a set of basically Fourier harmonics for this symmetry group. Okay, so well, any function of 4 variables in this case, which is my 4-point function, is in principle. Okay, so it is a function of 4 variables. Because of conformal invariance, it actually depends on trivially only 2 conformal cross sections. Okay, so now any function of these 2 conformal cross sections can be decomposed into basis of conformal partial waves. So this means that this correlator can be expressed. Now, this set of conformal partial waves is spanned by sort of known in any number of dimensions representations of the symmetry group. And basically, I will write it the following. There is some sum over spins, and then there is an integral of a mu, let's call it mu prime, 0 to infinity, with some weight of mu times this conformal partial wave. And that also depends on mu phi in this case. Okay, so this function conformal partial wave is the analog of my Fourier harmonic that now depends on 2 variables. Okay, it's some complicated function. Some dimensions is known explicitly what it is, but it's a function that studied very well, say in the recent conformal booster privilege. And all dynamical information is contained inside of this f of mu. Okay. So now the claim is that, and I want to, sorry, let me first call this function rho of mu. Okay. Now this is something that again can be done for any conformal field theory, and in principle it is done in Euclidean AdS. And then there it's known what are the analytic properties of this rho of mu. So this rho of mu turns out to be metamorphic. Okay, and then if we draw, say it's in a plane of this delta over d over 2, say plus I nu. So this is my integral goes like this. Okay, then poles. So this function in AdS can be taken to be symmetric with respect to the reflection of these points, and there will be some poles on the real delta axis that are called the spectrum of operators in the corresponding conformal field theory. Okay, this is just what happens in CFT, and that happens in AdS. And in AdS, these poles would encode the spectrum of states that our theory can have in AdS. Okay.
So half integral in nu, or does it go all the way down?
Well, again, I wrote it like this because I think principle. So this is the principal series contribution. Okay, there could be other representations. Never mind them. And then I think principal series are spanned from 0 to infinity. But here we can just put some 1/2 and expand it from minus infinity to infinity because this rho is the shadow symmetric and conformal partial wave is also shadow symmetric. Okay, good. But the reason I wrote it in that way is that in the theta, so there is some ambiguity in how you expand it to the full line, right? Because I think the real representation theory statement that the integral is from 0 to infinity. So now the claim is that in the theta we can expand it extend it to the whole real line in a slightly different way, and this is the object I want to call mu. So that it has somewhat this f has somewhat different analytic properties. Namely, it is, first of all, it's also metamorphic, okay, and then it has poles only on this side, and maybe, well, it has poles in principle anywhere in this plane on the other side, and maybe poles here on the real line between 0 and d over 2.
Do we know this or are we imposing this?
Good. So it is, well, okay, I think it's true. The proof, I wouldn't say that there is like a full proof. There are some arguments why that should be true. Again, let me say the result, and then maybe I can again say why I think this should be true. It's true in all the examples that we have, and there is some motivation why I think this should be just true non-perturbative. Okay, let me make the statement first. Good. So this is where poles of this. First of all, just the statement that it is, the statement that it is metamorphic, that is already a very non-trivial statement for the Sitter space. And again, there is the proof for it being metamorphic comes from us being able to rewrite the theories for Euclidean AdS, where it will be metamorphic. Okay, just at least diagram by diagram, I think it will be metamorphic. Now, it is a weird theory in Euclidean AdS, so maybe there is some subtlety with it. That theory itself does not have a Lorentzian AdS interpretation. So maybe some of the things we could not guarantee for that theory. And again, non-perturbative of the status of that theory, that is, where did it go, this theory? We cannot see it, right? Whatever this, say this type of theory, right? We kind of, okay, we should not bet on anything. But when we do perturbation theory, of course, we'll generate some same things that we have in AdS, okay? So it will be metamorphic. Now, where this structure, here I say, okay, if it's metamorphic, can have any type of poles over here. The fact that I can rewrite any function, basically, that it does not have poles on this side, this is almost true modular, screwing up the asymptotic behavior. Okay, there are some conditions on asymptotic behavior of this function. So I think that this asymptotic behavior can always be fixed by just having this poles over here, which are also allowed unitary representations from the Sitter point of view. But that's not proven.
You need any additional input about the large mu behavior?
Well, it is, it is a little bit of a subtle point, right? There is conversions proper. There are some subtleties with conversions of these integrals.
Yeah. So let me ask, maybe in AdS, is it like the stuff that you're saying in DS is like, okay, we have examples. In AdS, I figured we have more. What is known about this row of nu in AdS? Is it known that it's definitely meromorphic?
Yeah, because that comes from.
Even when you include loops in AdS?
Yeah, well, I think that in AdS, this is just the conformal partial wave analysis, whatever, OP inversion formula, all this business, right?
Conformal partial wave analysis doesn't tell you that it has to be just poles.
No, but they operate, I mean, if we believe in the operator product, OP inversion formula, right? This is what I'm doing here, going from the phi's to rho is what's called a capital C, I guess, in the papers of right on OP inversion. So going from correlator to rho, how do we go, right? We take so rho is an integral of
F compactness, I guess. You're saying the spectrum is discrete.
Yes, and then if of course I assume that CFT has a discrete spectrum, then the spectrum should be discrete.
There you're saying, so there it's crucial, like for you to deform and say, it has to be this, you have to say something about what nu does at I infinity, and there you're saying it's known.
Well, and there is some there is an operator state correspondence, right? So that's why we know that the spectrum should be discrete. That's why this thing should be metamorphic. And the convergence properties, okay, there are some subtleties with convergence of this integral for some coincident points, right? So this is, and we integrate dx1, dx2, dx4, and there are also some related subtleties with convergence of this integral when nu goes to infinity. But basically the point is that when these external operators themselves lie on principal series, then this convergence property is understood. Now, if they do not lie on principal series, then you play with some analytic continuation and you pick up some contributions. So you maybe need to deform your contour a little bit. Okay. So it is sort of similar here with the claim that convergence will be fine as long as you draw your contour basically like this, and possibly pick up some poles that right from well, that is I'm drawing here the say j equals 0 part. Okay, let's forget about j. Okay, I should really wrap up. So the statement that some parts of it is proven some by example is that thing is metamorphic. It has this analytic structure, which basically I want to say is very similar to, we call this f as a spectral amplitude, because it kind of has, we want to say that it has properties as an amplitude in flat space. There is like some physical sheet where it's analytic. There are some real poles which are like stable particles, and then there are poles that are in principle anywhere in the complex plane, and these are like resonances. Okay, so that's basically the picture that we're trying to throw here.
So these poles on the real line would correspond to particles in the complementary series?
Yes, yes, yes.
Is there a way to see that there has to be particles with masses along the, like, how do you interpret them in the space-time?
Let me get back to this in a second. Okay, I just say one more thing. So where the unitarity is, okay, it's almost written that, but unitarity, if we go back to this object rho also happens to be the imaginary part of f, by the way. Okay, and this rho is actually positive. So that's the positivity, that's the unitarity in the zero space. And that's, again, this is not so surprising. So this is different because we cannot have unitarity, usually in say normal unitary CFT or in AdS, unitarity, that was the reality, some unitarity conditions on where these poles can be, and then positivity of residues of this function rho. Okay.
Because of I in the Lagrangian doesn't screw with it.
No, they do. That's why these poles are in the complex plane and their residues can be whatever you want. But instead you get a different kind of positivity here, which is the positivity of the imaginary part of this f, or in other words, of rho. Okay? So that's how unitarity manifests itself. And that's actually something that can be proven non-perturbatively. Okay? So unitarity, so this part is true non-perturbatively. The statement that I made, this thing, okay, I said what the status is, yeah.
Even non-perturbatively in Euclidean AdS.
No. This thing, the proof of this thing has nothing to do with the Euclidean AdS Lagrangian. It's just some argument, okay, that again I can explain in the zeta space directly, and that is true non-perturbative. Okay? This part relies on the, so maybe I should, these parts come together. This is completely independent of the first part. This guy depends on this, and hence, proof is, I think, in perturbation theory. And maybe the last thing I want to say, and also answer your question, is that we go back to our example, where we actually calculated this f, the whole thing, and okay, this is the conformal partial wave, the rest is f. Okay, this f is some sine, some gamma functions, and then there is this f tilde, okay, where it is written over here, and you see that this f tilde is really very, very similar to the answer to the flat space amplitude, where this b is the bubble function in the zeta space. This b is just some representation of the bubble, which is the kind of an analog of what I was calling sigma in flat space. And first of all, you see that it's indeed metamorphic. Okay, all these functions here are metamorphic. So it is metamorphic. And it has poles where indicated. And basically the point is that there will be a pole, if the coupling is small, there will be a pole very close to the real line, but not exactly on the real line, which is where basically our spectral parameter passes the value of nu for the heavy sigma particle. And okay, near here we will of course see some sort of bump in the spectral density. And there is a very close relation to, say this bump can be positive, but actually this bump can also have some form like this. It can be mostly negative. And if this bump was too high, it would violate unitarity, it would violate positivity, but it doesn't, again, same as in flat space, amplitude never becomes bigger than 1 in some units. So same happens here. There's some, when we try to crank up the coupling, the width also grows, and this thing becomes order 1, but never larger than 1. As okay, check from this formula. It's kind of not obvious, but you can trust me this. So basically, we checked in this theory. We did these calculations and resummed this one with propagators and checked all these properties that I talked about.
Is the positivity of rho enough to claim unitary, or you need to also have some rule for the rho?
Yeah, well, very good question. Answer is that I don't know, yes, I don't know. I think it is a strong requirement. Of course, you need to impose it on all correlation functions. And in particular, correlation functions of different fields where it will be a bit more complicated. You have some matrix of correlation functions that have some positive determinant. So it sounds like a strong property, but if it is, so it's definitely a necessary property. If it is sufficient, yeah, I do not know. Do we need something else, or this exhausts, at least for quantum field series and the series? I want to think about it, but I don't know.
Yeah, because positivity naively says that rho admits status of being a probability density, sort of, for each mode number. But usually unitary means that you don't violate the sum.
Well, you see, you can, good. So probably, the question is, if we also impose something else that is coming from, quantum field theory, is that enough? Because you see, you can trade, usually when you violate unitarity, at least in quantum field theory, you can say, oh, unitarity is like my Lagrangian is Hermitian, or my Hamiltonian is Hermitian, right? But then if you, let's say, what's non-Hermitian Hamiltonian? Well, let's put some theory, let's make the coupling G complex or something. That will be non-Hermitian. But that you can always compensate for by kind of rotating away by rotating the sigma field. So you can, in some simple examples where you have non-unitarity, you can either express it as Hamiltonian being non-Hermitian, or some state having negative norm, right? Because just if you say say a finite dimensional Hilbert space, roughly speaking, right? There is some cell of the Hamiltonian that's not Hermitian, you can get rid of it by giving some state in negative norm.
Although those two have a slightly different, subtle difference, but anyway.
Yeah, okay, that's why I'm not making a claim, but kind of, roughly it's this thing. So that's why I'm saying that if you had some non-Hermitian Hamiltonian, then you would also see, there will be some direction in which rho will be non-positive, which kind of amounts, to having that state negative norm. But I'm not making a claim here.
Right, for example, in just the field theory in flat space-time, if a field appearing in the theory does satisfy canonical computation relation, then you can prove non-perturbatively that this thing satisfies some rule, like integrate to 1 property.
Yeah.
But anyway.
Yeah, I do not know what the analog of, so there's kind of two notions of probability, and probability should be positive and should sum up to 1.
Yes.
So that's then being positive. I do not know the analog of the statement that should integrate. Other questions? So I answered your question, I hope, that you asked what is the interpretation of these complex poles. I said that in a weakly coupled theory, well, they become like resonance. More generally, I didn't fully answer your question. I have something more to say. There is again a conjecture. So there is no, okay, let me even write it. No operator state correspondence in the series space. Because states, they live on this line over here on principal series, they're a continuum of states. And that's why positivity related to the states. While operators, in my operator product expansion, I said explicitly, we can generate from this picture operator product expansion by correlation by pulling the contour to one side, okay? We'll generate a set of operators with complex anomalous dimensions, generically. And the conjecture again, so there are many conjectures here. The conjecture is that they correspond to quasi-normal modes of my theory in the Sitter space. Quasi-normal modes of the static patch. So here we can circle back a little bit to this diagram. Okay, I don't, but I'll draw it again. So you remember there was this static patch thing that we didn't study much. But the idea is that actually all the spectrum of operators can be read off just by studying how various perturbations in the static patch decay and fall behind the cosmological horizon. So the way the exponents with which perturbations inside the static patch decay can be called again, definition is subtle, but roughly they correspond to what can be called quasi-normal modes of the static patch. And quasi-normal modes generically have real and imaginary parts. And that's the idea that they actually correspond to the full set of operators, to the full set of poles.
So did you check that in the simple examples? Or?
No, because nobody, including me, has, for free theory it's true. Okay, in this interacting example, nobody checked it because nobody has calculated in quasi-normal modes in interactive theory. So there are people I know who are working on it now, calculating, and then once they calculate, they will match, and we'll see if it works. But not yet. Yeah.
Are there more questions?
Can you bound like coefficients for EFTs with some sort of positivity constraint?
Yeah, again, good question. So in this paper that I mentioned by Joao, Kamran, and Matthijs, this paper from PFL, they do like a sort of simple version of Bootstrap using that positivity, but they do it just for a free theory. So they have some generalized free field, and then they put some bounds on the spectral density. But again, this is like one example. Nobody tried so far for interacting theory. I'm sure it can be pushed. I do not know if there will be results, but also recently there was a paper by people from IAS, by Perter, Dalimil, forgetting the third author, his name, but they did the Sirdip, right? Sirdip, right? Good. Perter, Dalimil, and Sirdip. So they did bootstrap analysis for the spectrum of Laplace operator on hyperbolic manifold. Basically, the positivity condition that they have there is again positivity of this, basically analog of this, direct analog of this positivity condition. And so these tools, they can be applied to this problem, I think, and yeah. I don't know. It sounds, yeah, with this bootstrap things, I do not know. Sometimes magically they produce, extremely strong results. Like in their case, they put extremely strong bounds, right, from this. So this is definitely encouraging that one can also put some bounds on quantum field theory synthesizer using this bootstrap, but beyond this, the free theory case studied by PFL people, that hasn't been done.
Okay, maybe we can thank the speaker. I'll stop the recording.
Is there some analog of
well, this is in a sense, you see, for free particles, when you have free particles, all of them, and again, there is an analog for different spins.